One side, you've got our everyday world. Solid, predictable cause and effect. You throw a ball, it goes where you expect. Seems simple.
Right. Classical physics works beautifully for that.
But then there's the quantum realm underneath it all. And that's just, well, it's bizarre. Probabilities, things being in multiple states at once.
Weirdness, yeah. Pure quantum weirdness. It feels totally separate.
Exactly. So the big question we're diving into today is, how on earth does our solid, predictable world actually, emerge from all that quantum strangeness?
That's the core puzzle. And it's something physicists have wrestled with for ages. But the insight we're looking at today suggests it's not a dead end. There is a connection.
Okay, so what's the mission here? What are we trying to uncover?
Our mission, really, is to show how these incredibly tiny de Broglie wavelengths, something fundamental to every particle, how they actually build the foundation for the causal reality you experience, the tangible world.
De Broglie wavelengths. Broglie, right. Planck's constant over momentum.
That's the one. Every particle has this wave-like nature.
So we're aiming to bridge these two worlds, and we're using insights from de Broglie wavelength, unveiling macro-world causality. What's the key idea from that source? Because, for so long, the gap just seemed huge.
It did seem immense.
Take that baseball again. You throw it, it follows a nice, clean arc.
Predictable.
It doesn't suddenly tunnel through the wall or appear in the catcher's mitt and behind the backstop at the same time.
No, definitely not. It behaves classically. But quantum mechanics insists everything, even the baseball, has that wave nature, defined by its de Broglie wavelength.
Right, but here's the kicker, isn't it? For something big like a baseball, that wavelength is, well, it's almost nothing.
It's unbelievably small. We're talking, what, 10 to the minus 34 meters? Something like that?
Which is just staggeringly tiny. Way smaller than an atom's nucleus.
Infinitesimally small, yeah. And that's why we don't see baseballs acting like waves. The effect is negligible at our scale.
So it's easy to just dismiss it then, say, okay, it's there, but it doesn't matter for big stuff.
You could dismiss it, but that would be missing the whole point.
Yeah.
The source argues that the causality we see, the predictable nature of the world, it isn't separate from quantum mechanics. It emerges from it.
Emerges.
Yeah, it's born from the collective behavior of all those underlying quantum waves.
Yeah.
That's the real aha moment we're chasing today. It reframes what solid even means.
Okay, that's a pretty profound claim. Causality isn't fundamental in the way we think, but it emerges from the quantum level. How does that even begin to happen? What are the bridging concepts?
It seems counterintuitive, but there's an elegant pathway. The deep dive highlights two main concepts working together: the correspondence principle and something called quantum decoherence.
Right. The correspondence principle and quantum decoherence. Let's take the first one. Correspondence principle. Niels Bohr, wasn't it?
That's right. Bohr formulated it. Essentially, it's a consistency check. It demands that quantum mechanics has to give you the same answers as classical mechanics when you're dealing with large systems or large quantum numbers.
So as things get bigger, quantum physics has to smoothly blend into the classical physics we already know. It can't just be a sudden break.
Exactly. It ensures the universe doesn't have two contradictory sets of rules. It has to be consistent across scales.
And how does that work for, say, our baseball?
Well, for large objects, the possible energy levels described by quantum mechanics get incredibly close together. So close they form what's practically a continuum.
So the distinct quantum steps kind of blur into a smooth range like classical physics assumes.
Precisely. The discreteness fades away for large energies and large objects. And think about the sheer number of particles in a baseball. Trillions upon trillions.
Okay, yeah. A mind-boggling number.
Each with its own tiny de Broglie wavelength, its own wave function. But when you put them all together, their collective behavior, statistically speaking, ends up looking exactly like Newton's laws predict.
So the individual quantum weirdness gets averaged out.
In a way, yes. The probability distributions described by their wave functions become incredibly sharp, tightly focused around a classical path. Any quantum fuzziness becomes utterly insignificant.
Wow. So it's like the sheer numbers wash out the quantum effects for the object as a whole.
That's a good way to put it.
Yeah.
The correspondence principle sets the stage, ensuring the theories align at the right scale, but then there's decoherence. That's the mechanism that actively makes it happen in the messy real world.
Decoherence. Okay, what's the problem it solves?
The problem is that quantum systems, with their superposition and wave-like behavior, can really only maintain those properties if they're perfectly isolated.
Which nothing ever is, right?
Yeah.
Especially not macroscopic objects.
Absolutely not. Our baseball is constantly getting bombarded, photons hitting it, air molecules bouncing off it.
Even internal vibrations within the baseball itself.
Exactly. Every single one of those interactions acts like a tiny measurement, a continuous probing of the baseball's state.
And measurements in quantum mechanics are famous for, well, for changing things, making possibilities collapse into one reality.
Precisely. Each interaction entangles the baseball's quantum state with the state of whatever it interacted with, a photon, an air molecule. This entanglement essentially leaks the baseball's quantum coherence out into the environment.
Leaks it out, so the quantumness spreads thin.
That's a great way to think about it. The information about the superposition, about all the possibilities, gets dispersed into the incredibly complex state of the environment. And for us, that information becomes effectively lost.
And the result of all this leakage and entanglement?
The result is what looks like a very rapid collapse of the wave function. All those potential quantum states vanish, leaving just one single, well-defined classical state. The baseball is here, with this momentum, not potentially elsewhere.
And this isn't some mysterious process, it's just physics.
It's a direct consequence of applying the Schrödinger equation, the master equation of quantum evolution, to a large system interacting with its environment. It's complex, but not mystical.
And it happens fast.
Incredibly fast. For a macroscopic object, the time scale for decoherence is so short, it's practically instantaneous. For all intents and purposes, the baseball is always in a definite state, following that predictable classical path.
Okay, so let's try and trace that causal chain then. From the quantum foundation to the world we see, how does it flow?
Okay, step one, fundamental reality. Every particle, every object has a de Broglie wavelength. The wave-particle duality is inherent.
Got it. Baked in from the start.
Step two, at the micro level, things are governed by quantum mechanics. Probabilities, wave functions, Schrödinger's equation.
Standard quantum rules.
Step three, scale matters. As particles clump together into a big object, the correspondence principle ensures that the overall quantum description starts to look classical because of the sheer numbers and energy levels involved.
Aligning the frameworks.
Step four, the environment kicks in. Constant interactions cause rapid decoherence.
The leakage we talked about.
Yes, decoherence suppresses superposition and interference. It effectively forces the object to choose a single classical state out of all quantum possibilities.
Like pruning away the other branches of reality.
Exactly. And step five, emergent classicality. Because decoherence is continuous and super fast, the object stays in a well-defined state with a definite position and momentum, evolving predictably according to classical laws.
So the causality we observe isn't separate from quantum mechanics, it's an output, an emergent property.
Precisely. It emerges directly from the underlying quantum reality via decoherence.
That makes a lot of sense. Now, the source also mentions an alternative view, or maybe a complementary one, the Broglie-Bohm theory.
Ah, yes, pilot wave theory. It offers a different but supportive perspective on this causal link.
How does it differ? What's the core idea?
Well, standard quantum mechanics is often interpreted. Probabilistically, particles don't have definite properties until measured. The Broglie-Bohm theory says no, particles always have definite positions.
Always. So where does the wave function come in?
The wave function acts as a pilot wave. It's a real physical wave that guides the particle along its path. The particle surfs the pilot wave, so to speak.
Okay. So the particle has a definite position, but its trajectory is determined by this underlying wave.
Exactly. And the wave itself still evolves according to the Schrödinger equation.
So what does that do to the probabilities? If the position is definite, why does quantum mechanics seem probabilistic?
In the de Broglie-Bohm view, the probability arises from our ignorance. We don't know the particle's precise starting position within the wave. If we did, the theory is fully deterministic. The apparent randomness is just due to unknown initial conditions.
I see. So it provides a completely deterministic picture, even at the quantum level.
Yes, and an explicitly causal one. There's a clear cause, the pilot wave and initial position, leading to a definite effect, the particle's trajectory. This naturally extends to the macro world, giving a very solid-looking chain of causality from the quantum up to the classical.
So it reinforces the idea that there's no fundamental break between the quantum and classical realms.
It strongly supports that, yes.
Yeah?
It offers a way to visualize that unbroken causal link.
So pulling it all together, it's quite remarkable, these minuscule de Broglie wavelengths, seemingly irrelevant for big objects. They don't actually sever the connection to our world through things like the correspondence principle and, crucially, decoherence.
And may be helped by thinking about pilot waves.
Great. A clear, logical pathway emerges. From the quantum weirdness to classical predictability, it almost feels inevitable.
It really does. The source paints a picture where the classical world, with its clear cause and effect, isn't just compatible with the quantum realm, it's a necessary consequence of it.
Which really speaks to a deep unity in physics, across all scales, doesn't it?
A fundamental, unbroken unity. That's the implication.
So here's something to think about. If our solid, predictable world is truly just an emergent feature of the quantum dance beneath, what does that really mean for the solidness of things? Knowing that everything around you is constantly teetering on the edge of quantum probability, only held in check, nudged into certainty by its constant conversation with the environment, does that change how you see the world?